On the last day of Chapter 8, Section 8.4, Day 2, we finally get a glimpse of the usefulness of a logarithm. We've been learning a logarithm, we've been looking at the details, the rules of logarithms. You can do the work, but you're wondering, okay, what is a logarithm? I keep challenging you guys to think graphically, but then you're like, okay, great, I know what the graph of a log looks like, but tell me, what possibly can they be good for? This is not the only thing that they're good for. This is a very simple version of what they're good for, but at least it gives you a tiny spark of, oh, logarithms, they're very strange, they're very abstract, but they do have a real purpose in math and sciences. So here's how we go. So let's say we were supposed to solve another equation, and this equation is an exponential equation, and here's how it goes. It goes 4.2 raised to some power is 28. We're trying to figure out what that power is, and here's where right away you're like, oh, this isn't that easy. So I'm just going to write a different one. Let's say it was only 4. You had to solve this exponential equation. 4 to some power is 16. You'd be like, this is easy. It's 2. Here's where the problem comes in. What we have is 4.2, then a 28. What would this power be? It's not a whole number. It's some decimal number in here, probably like a long decimal. And how would you possibly figure that out? The good old elementary school trial and error will not cut it. So here is where we enter the power of a logarithm. What you see in the PDF notes is we began by simply logging both sides. And that is 110% legal. It's the old what you do to one side, you do to the other. And okay, the whole thing is in balance because we just did a log on both sides, even though it looks strange. Now, remember your rules of logarithms. You can take this power down. We can write it down as a coefficient. You can move it up if you want. Now is the time to want to move it down. I am going to isolate x. Right now where my marker is, it's assumed to be a multiply. So I'm going to divide. And I'm going to have a log 28 divided by log 4.2. Now, right now, you may want to pause the video for just a second and grab your calculator. Any calculator that's scientific will do, because this is something that can simply be typed in. It's assumed to be a base of 10. Every little calculator that has a log button is designed that way. You don't need one of the big graphic calculators. And if you type in log 28, go divide log 4.2, what you would see is 2.322, and then more decimals. We'll just go to 3 decimal places. That's what you do in advanced placement calculus anyway. This is our solution. If we took this and put it in for x, when 4.2 raise it to the power of 2.322, it would come out pretty darn close to 28. It's not perfect because we rounded a bit. That is a useful application of logarithms. Now, sorry, I have to squeeze over a bit. Here's our next guy. 5 to some power is 87. It is not 5 squared because that would be 25. It is not 5 cubed because that would be 125. So it's some number between 2 and 3. That's what we definitely know. Well, how could you possibly solve it? Enter the logarithm. It is a very powerful tool, even though sometimes you get annoyed with it because you're wondering what the heck is actually a logarithm. Here's what we could do. We could just log both sides. That is legal. The math police are not going to come in and arrest us. We can drop our power down. We can divide the log 5 to the other side because it's the opposite of multiply. And for the first time in this question, we can grab our calculator out and do this division. If we just type in straight out log 87 divided by log 5, we get x is equal to 2.775. Now, I know that only a few of you might have taken a chemistry course already, like Chem 30, but if you imagine chemistry, this could easily happen in some of the calculations you're making in labs. So now let's go to number 2, the end of the entire chapter, where we're going to solve equations, the exponential equations, and I called it a higher level. And for number 2a, I just want to clearly show you guys what would have been written on the board. It was a 4, then a 5 to the x minus 2, and then 1,100. This is the way the question would have originally looked. The PDF notes show the first step at the same time. What we are going to do to solve this guy is apply the same principle, but we have to just do a tiny bit of prep first. We have to get rid of this 4. That's what's in your notes. It shows a divide by 4. It just doesn't show the color as the first step. And what happens is, if you divide the 4 off to the other side, 1,100 divided by 4, 275, now we're right there. we're right where we can do a log on both sides. This is assumed to be a base of 10. And as long as you log both sides, you're not breaking any rules. Everything's good. It's an equality still. We can bring our power down. I'm going to put it in a bracket. Now, don't panic. I know there's just one little thing that might be bothering you. It's this 2. Just relax. If we isolate the x minus 2, if we divide the log 5 over, so we have log 275 divided by log 5, sorry, that looks like a power. What we have is something that can be typed in. This would be the first time we'd use our calculator. If we type in log 275 divided by log 5, it comes out to be 3.499. And then our final step is just to add the 2 over. So our final answer would be 5.499 when we add the 2 over, and we've just done it. If we go back to the original equation, 5.499 can be put in, and this would be an equality. And so now for our final example, we go to probably the highest level that you'd have to do at the high school level, because there's 2 variables. We're going to use our calculator a little bit earlier than normal. So we have 2x minus 1 is equal to 3x plus 2. And we begin by applying the logarithm right away. There's nothing else to really do. So we log both sides. We have log 4, 2x minus 1. We have log 3, and then an x plus 2. We can take the powers down. Very, very useful rule in logarithms that's been proven many times over. But now here's where we have to do a change. Instead of just dividing the log 4 over or dividing the log 3 over, we've got a little issue. That is that we have 2 variables. So that process won't work, but we're going to do something different. What we're actually going to do is use our calculators right now. If you type in log 4, remembering it's a base of 10, it is 0.602. If we type in log 3, it's going to be a little bit smaller, and it is 0.477. Here's where we are. What we could simply do is solve this like an equation. I'll call it a grade 9 equation, but probably you don't use decimals like this in grade 9. We are going to take 0.602 and do the distributive property. We're going to take 0.477 and distribute it to this bracket. And here's what we would be left with. If we distribute it here, it is 1.204x. Right here would be just a minus 0.602. On this side, when I distribute it, 0.477x. And then when you distribute it to the 3 and multiply, it is 0.954. And then even though this looks strange, here's where we are. We could easily collect our x's. So I'm going to take this 0.477x and minus it to the 1.204x to get a 0.727x. I'm going to take this 0.602 as a number and bring it to the other side. 1.556 when we add it to the 0.954. And now our grand finale is to divide this over to the other side for a 2.140, and we've solved the equation. Now, before we finish, I'm going to just do the reminder. I'm going to erase just for a minute, and you guys don't erase. And I just want to show you guys the idea. Okay? So if, again, at the end of the chapter, somebody says, what the heck is a logarithm? Well, a logarithm is a graph, and you're probably tired of me drawing this little thing that doesn't go into your notes. So right here, this can be any log graph. This could be y equals log, and it could be a base of 2, an x, and whatever you want, right? So here's the idea. Log of 3 is just some value, okay? It's like saying if I go out to 1, 2, 3, here's 3, log of 3 is some height. What is that height right there? 0.477. So hopefully that calms you down a little bit as you're solving these equations. You won't use that, but it starts to tie it in. And that is the end of chapter 8.